And follows on. So I hope I'm loud enough, legible enough, that everyone can understand what I'm saying. So I'm Monu from batch 20. I'm a part of School of Physical Sciences. For those who know me and don't know me. And today's topic is magnetic field of. So the point of this talk is to give a feeling of what's this all about. For those of you who know things, some statements or explanations may seem simplistic or even reductive, but I'll ask forgiveness before because since this is a general audience, I'll tailor my talk accordingly. So kindly forgive if you are not satisfied with the level of detail I have in this talk. I am not satisfied with the detail, but I'll go on anyway. Uh, Please keep your questions towards the end of the talk. So if you have anything pressing, like if you have a piece of paper or your phone, you can note down the topic and you can ask me later. So I'll request you to not ask questions in the middle, preferably. Now, magnetic fields of stars. So fields in general, like physical fields in general, and magnetic fields in particular, are things of wonder. So I like excuse my language, but it's almost like magic to me because if you think about magnetic fields, like if you really think about it, so start from very naive sort of thinking. If you compare electric fields, you are told that charges are there and that's why you have electric field. So there's an electron or a proton, whatever. And then the space around it, there's electric field. Now, if you ask why is there, like how does the electric field come from? a non-answer. This field. As you go along, like field theory has some answer. So those of you who know particles and fields, like the boundaries become fuzzy later on. But this is not the case for magnetic field. Like since monopoles do not exist, you won't have, and you don't have the analog of charge. So it's a very vague thing, but the effects you can see, the effects are wonderful. Like you have magnets, you have superconductors, the trains are running on magnets, you can do cool stuff using superconductors, and so on and so forth. The studies, like the fields of study, are numerous. So Cooper Bears, superconductors. There was a hype going on a bit like recently, that normal, like room temperature superconductors. So that fields are like, magnetic field have a great stuff, and hence I chose this topic. But if you're doing something, do it big. So stars and magnetic fields. Now, one thing, like from the top of the head, the coolest thing about magnetic fields or fields in general are the simulations or models. So you can do this cool art sort of thing when you are studying magnetic fields, and this is nice to look at. When you are stuck at some point and you are not getting any answers, you are bored, like banging your head on a wall. Look at this cool art, and this is why we are doing it. Now, the outline of my talk. We'll start with, since we are looking for magnetic fields of large bodies. The first question is, where do I look? Like I can't look at things on Earth or in this room or whatever. So where do you look? Then what to look for? Like since you know that I want to look at in this direction. So now the next question is, what are you looking for in that direction? How will you look at it? Then once you have seen stuff, as a natural question to any physicist, once you have seen stuff and systematically seen stuff, you think that, can I predict this or not? So you think about how does it happen and try to model it. So that's the part of how does it happen. And then we'll look at some stars, starting with our sun, the closest star, and really our star. Then we'll look at white dwarfs, and in the end, I'll briefly mention some things about neutron stars and magnetar particles. So, where to look? Uh, Obviously, you look uh, night sky, in the outer space, obviously, and you use telescopes or whatever. So, where to look? The easy answer for now, look in the outer space. So, get your telescopes, point them to outer space, and let's go looking. Before that, since you are looking at stars, not all stars are the same. Anyone knows what this diagram called? Yeah, okay. So I don't remember the name, but he does. So we believe him. And so the classification scale is it's written O. Okay. So the classification scale, the system classification system is more like even classification system. It goes from, so the letters are assigned. So O is for the coolest star. It goes up to M and then T, and it's usually for the hottest star. And then, so depending on the temperature, you get, since you are looking at the light from the star, so that is why there is spectral classifications. O is the hottest. Oh, yeah. So, correction. So O is the hottest, M is the, so we split this. O is the hottest, as we said. This, adding to the spectral classification, there is a luminosity, and on the higher side, like uh, the top is corresponding to the most massive stars found there. And as we go below, we get lower and lower masses. So, thing to think about for you all is the correlation between mass and luminosity. Since I've told you that higher the luminosity, higher the corresponding mass. So, why is there? There is some correlation, obviously, but why? Do you think about that? I will not say. So this is the stellar classification, and when we are looking at stars for studying magnetic fields, we'll keep this in mind. This will come back again and again. Earth somewhere, Earth lies somewhere around here, so it's G to 5. So along with the letters for spectral classification, there's further division from 0 to 9. So there, suppose F. So F0, F1, F2, F2, 3, 4, and so on. So F0 would be the coolest, F9 would be the hottest. So Earth is G25. Now, you know where to look, what to look for. So you know you are looking at stars now, but what exactly are you looking at and how? If I told you just look at stars, you'll have a photo of a star and you tell me, you'll bring it to me and tell me about the magnetic field of that star. So I can't do anything. I need to be more specific and more particular as to what you are looking for. This will come back again. This is to entice you about what to look for and how as well. Now, some hints. So like at the starting point, you are clueless as to what do I look for in a star so as to study its magnetic field. So we take some clues from our sun, and anyone has any idea who drew this picture? I don't know. Maybe. So hints from our sun. Galileo saw sunspots. So the dark spot would be sunspots. Then somewhere for differential rotation in 1630, as back as 1630. That's great. Then there's cyclical activity. So some of you may know about solar cycles that will come back later in this talk. So we have some hints as to what to look for in a star so as to study its magnetic field. So we use that and then build devices accordingly. So spectral classification, we are looking at the spectral lines from the star, and then using that we are trying to get some idea about the magnetic field of the thing we are looking at. So one thing we use is a magnetograph. It's a device that then it reads. So and the result from the magnetograph is called a magnetogram. As you can read, its spatial variations in the strength of the magnetic field. So how it works basically is it will read the polarization of the light which you are getting. So suppose there's a star that way and the light is coming this way. I'll put some device here, read the polarization of light which I'm getting. And then from that polarization, I calculate the magnetic fields. How? We'll see. So these are some of the magnetograms. This is both are taken from Mount Wilson telescope. It is one of the largest such telescopes which measure this. So these black spots and white spots, black and white is the polarity thing. So black is negative and white is positive. So this like first of all, you need to appreciate that we have achieved this. We have achieved a magnetic map of the whole sun, and it's not easy, let me tell you. So, this in particular has a lot going on, so a lot of dark and bright spots. This is more or less granular, except this. So these points are points of interest, and we'll see what is happening later on. As I said, we need to appreciate that from this we have this. So at the start, after knew where to look, we were here. We were seeing this, and now since we know what to look for and how, we have achieved this. So from a photo of a star, you get a magnetic map, a field map of the whole body. That's amazing. So magnetograms are of two types. Uh, the usual normal basic magnetograms, and the second one is vectorial magnetograms. So as I said, I study the light polarization. From there, so the line of sight that tells me to be circular the circular polarized light which I am seeing, that will tell me the magnetic field along the line of sight of direction, and the linear polarized light will tell me the transverse magnetic field. So I'm using different kinds of polarized light to get an idea about the strength of magnetic fields in different directions. How these two are related, we'll see. So vectorial magnetograms. So as I said, different directions, like different components of magnetic field. This is azimuthal magnetic field. This is meridional. This is radial. So different components depending on which polarization you are studying. The star in case here is HR1098, some details about the star. And as I said, points of interest. So those were star spots, and those are regions of dense magnetic field. Why we will see later. So giant star spots at higher latitudes, as you can see, the colors you can see in all the images. Now you have magnetograms. One more thing which you can do is Doppler imaging. So as you all, like most of you could know, Doppler shifts. You can see the change in frequency depending on the motion of the objects, depending on the relative motion between the objects, between the observer and the source. So that's what is at play here. So the body is rotating, right? So depending on the tangential velocity of the endpoint on the surface of the rotating body, there'll be, if it's going towards you or if it's going away from you, depending on that, there'll be a Doppler shift in the light you get. So you measure that, then you sort of know. Now, quick question to point out that we are talking about magnetic fields here. Why again Doppler imaging in here? So there's something called Zeeman effect, you would have heard. So Zeeman effect, or in some cases Harvey effect. Harvey effect is special cases where there is level crossing, even 0 feet. We'll keep that aside. But majorly Zeeman effect influences our spectral lines. So when we look at stars, we are mainly looking at the spectral lines, and depending on how much the spectral line has shifted, like if it has split or if it has broadened, we'll know that magnetic field is in play here. So Doppler imaging, more specifically Zeeman Doppler imaging (ZDI), that is used to measure magnetic fields at different spots. So one quick note, as I said, we are looking at rotation for relative motion between. So for Doppler imaging to work, we need relative motion, right? So and in our case, the relative motion is in rotation. So this method is mainly used for highly very quickly rotating bodies. The star is rotating very slow. The information will be achieved is very low. So mainly for very quickly rotating bodies. Now, wonder how you can extract magnetic fields from polarization. So there is something called Stokes parameter. and some of you may know. Optics guys may know something about Jones vector and Jones matrices. You generalize that and get Muller matrices. So we'll use that. So Stokes vector, we have, so if I use Stokes vector very quickly, four components. So the first component, so sometimes it is S0, S1 to 3, or sometimes it's I, Q, U, V. S naught or I is the total intensity of the light we are getting. And S1 or which is Q and S2 which is U, these two are related to the linear polarization of the light circular plane. S3 is the difference between right circular polarized light minus the left circular polarized light. So the difference in intensities between these two, that is my S3 or V. This is the electrical coordinates and then that. So how do you do this? So you have so make a magnetogram. The very first initial magnetograms were very simple. Like in a telescope, you put a beam splitting polarizer analyzer, and then from that you measure the intensities, and that's it. That's your magnetogram. So pair the polarizer and beam analyzer. Then you can now it has like a lot of modifications have been done, and there are much better magnetograms. But initially that was it. So once you have polarization, how do you get to the magnetic field? So again, this is a very difficult task if you get to it, because you need to know how the polarization is reaching from the star to your telescope, and to know that you need to know what's happening in the atmosphere of the star. So it's not as easy as I told you originally. Originally, it was very like happy-go-lucky type kind of thing that you know the polarization, you get the magnetism, but not so easy. So there are models of atmosphere of stars. Depending on so obviously you when you model something, then depending on that you introduce some parameters and then go on. So I've shown one such procedure there. It's not the only procedure. Different procedures have different calculations and efficiencies. So this calculation or this equation in particular is corresponding to something called Milne-Eddington model. The assumptions are as follows. So the ratio of line to continuum opacity is independent of depth, and the source of function is linear in optical terms. If you don't get it, forget it. Furthermore, assume that the magnetic field is constant in strength in the direction over the region of line formation. Quantum mechanical effects are ignored in the Muller matrix. So, optomechanical coupling should happen if you want to do quantum mechanical treatment, but if not, you can ignore it. And then the magnetic field is effectively strong enough that these do not occur. So, knowing all that jargon, which is not as important for now. Take this equation, I am giving it to you, and this is how radiation travels. So this is the transfer equation for polarized radiation which you get from the star to your telescope. Now, what are these terms you are seeing? Mu is the cos theta angle. So is the direction cosine of the radiation propagation vector. S is your Stokes matrix. That is fine. Identity. This is the Muller matrix. B is the source function. So how is the radiation generated from the star? This encodes information about that. And R is the ratio of line center opacity to continuum opacity. Now, if you have this equation, what do? Uh, Magnetic field, as I said, we want to measure magnetic field, so that enters to the Muller matrix. If you don't know what Muller matrix is, know that we proceed any use. So source functions, again, there is something that approximation made about the source function. This model which this procedure which I'm presenting, this was first done by Unno. He considered the most basic source function linear. So beta is a parameter, beta is a parameter. Tau is another parameter. This is some constant. So using this source function, he solved that equation. and we compare the components. And once you have these four equations, now your job is non-linear optimization. You solve for not M1, M2, and M3. Since you have these as measured and everything else, some are parameters, some are constants. So if you do all this at the end, then you get then you reach from polarization to magnetic. So it's not as easy, but still doable, roughly. Like not exactly accurate, but you get some idea. Now another thing which you can do apart from Doppler imaging is spectropolarimetry. It's sort of the same thing where you are looking at deviations in spectral line due to Zeeman effect and Allen effect. So, a reflection Zeeman effect. This is the equation for an atom in magnetic field. So, kinetic energy term, potential term, LS coupling term. Then this. So, Zeeman effect. There are types of Zeeman effect depending on the regime you are working in. So, weak field Zeeman effect. LS coupling dominates. These two terms are not there. Ignore the terms in the bracket. Only the upper terms, the weak field Zeeman effect. If the magnetic field is strong enough, this term dominates, and then you get something called partial Bach effect. And that is not Zeeman effect, but partial Bach effect. Then the last term gives you what is known as quadratic Zeeman effect. So there is different kinds of splittings you could see. So why I'm telling this is because if you have a bunch of data from your observation, you need to know how to make sense of it. So since the data, the information about magnetic field which is reaching you in the form of that data, they come from different points on all the star, and different points may correspond to different strength magnetic fields. So you need to know what may happen. So depending on that, you know what's going on in that area or what's going on in that area, depending on how much deviation you see in your spectral lines. So spectral polarimetry, all that. Okay. So at the end of all of this, you have achieved this. You have a photo like this, and what you can do now is make magnetic field patterns. So from this, you've gone to this, or from this, you've gone to this, which is amazing by the way. You are looking at a star, and now you can more or less accurately draw the field map by raw power calculation. That is amazing. So sunspots gave us the hint, and we got three things as I said. We could also look at differential rotation. Why this is important? We'll know later on. This will come back. So what we do is we look at uh, we track the relative motion to star spots. So it could be sunspots in case of sun. So different sunspots could be rotating with different velocities, which you may not expect at first glance, but it happens. So these two plots, the upper one and the mid one, are the latitude, the x-axis latitude, y-axis latitude, x-axis rotational phase. So these are two different timestamps, and you compare these, and you get this. So the phase shift and latitude. So you have to see that in this latitude region, there's a lot of shear going on. So this is very useful when you want to analytically see what's happening, try to create models for how the magnetic fields evolve. So you can use this later. As in continuation of the earlier slide, this is d omega and omega equilibrium. So you can this is a measure of shear of the star in consideration. Now, from photosphere, so all the events which we considered so far, they were of the photosphere. As in sunspots are on the photosphere, differential rotation also on the photosphere. But events there, far-reaching effects. So corona is also affected. You can see an example of that in X-ray emission. So events on the photosphere have far-reaching consequences, and this will come back to us later. Now, here so far you have some systematic idea of how to observe things. So, so far, if you see any star, if you look at any star, you can construct magnetic field maps. Now, the natural question to mind, or which should come to mind, is can I predict what is going to happen? This model, either you could observe over years, sometimes it takes years to get an accurate map, or if you have a good enough predictive model, you can make this. This is a generated model. So how does it happen really? Now, this is a two-part question. In all honesty, we are not going to address both of those in this talk. I'll cheat a bit and I'll hint at things, but will not really address both these. So, what are both these questions? So, first one, what happens actually when the star is forming during its formation stages to give it the field it has? First part is that, and that is really difficult to study. Uh, the second, even the observations are very. Second part, if you have any existing star and it has some magnetic field system, how does it evolve exactly? So all technicalities of its evolution, that's the second part. So I'm not going to address both of these. So I'm going to meander my way through these questions, but we'll see what we have. So now the answer. What? How does it happen? The easy way. It depends. So it goes like this. This answer goes anyway. Whatever the question, it depends. So this goes here as well. Now, what does it depend on exactly? Stellar classification comes back. So, since stars are not different, every star is unique in some sense. So is the magnetic field of them, more or less. So, when you start thinking about how does it happen, we need to start thinking about that for each and every star individually. So we'll not do that individually. We can group these, so it's not as difficult as it sounds. So we'll look at the models for magnetic field origin by way of classification. So first we'll look at intermediate mass stars, white dwarf and white dwarf. Then we'll see something about our sun. Then we'll see about neutron stars and magnetars. So and this is how it is studied. So you don't just pick a star randomly and then start studying. So the study has been stratified in terms of the stellar classification. So we'll go intermediate masses and white dwarfs. So in intermediate mass stars would be somewhere around the uh, middle or lower middle region of the scale which you just saw. And white dwarfs also lie from lower to max, the middle of the chart which you just saw. So we'll study the magnetic fields of those. And why I'll tell you. So A and B type stars, according to their classification. These stars, like these stars and white dwarfs as well, these are peculiar in the sense that the spectral lines you get are chemically very different. So, depending on the kind of spectral line you can get some idea of the element question. So, what's the element that? So, these types of stars give very different kinds of have very different kinds of elements in their atmosphere. As you expect, white dwarfs with their solar age in the evolution stage, they also have different elements in their atmosphere than you expect sun or sun-like stars. So the reason for heavy observation of these stars was that, like originally, it's not that when people were looking for studying magnetic fields, they chose these particularly. No, they were looking at these stars already, and since they had a lot of spectroscopy data, this was the first thing to look at. So a lot of study has been done around these stars in particular, except Sun, because Sun is, as you know, our Sun. So many of these kind of stars have high magnetic fields, around 300 gauss, and initially it was believed that only some of, like, not all AB stars are strongly magnetic, only some are. But then we saw that a lot more is going on. So MS stands for main sequence. Main sequence stars are somewhere around the middle of the chart which you just saw, the self classification chart. So white dwarfs are formed when the green star bursts and it evolves to a white ball. I'll skip this over very rapidly, but I assume you know how white balls are formed generally. So once the star has died, have a white dwarf. Like most of white dwarf like stars are formed from A B kind of stars or thereabouts. And what we have observed that a lot of these stars are highly magnetic. So 10 to 25%, that's a very high number even if you don't think that is. And about 30% of early type stars have large latitude, low luminous magnitude. This is significant, and why we'll see. Now, back to the question: how does it happen? Again, like, things are not exactly clear, and we don't exactly know how stuff happens. Like this way, like it's a work in progress, definitely. But what I present here is just some idea of what's the current belief about how things happen. So there are two major hypotheses about how magnetic fields orientate for stars. One is fossil field hypothesis, and the other is dynamo hypothesis. So uh, let's, if you like, if you ask normal physics student about a guess how many planets, okay, or what, he would, if he read somewhere or something, he would say that there's a fluid electromagnet inside the core. So the core is solid, iron core, molten layer around that, it's rotating, and then we get a magnetic field due to that. It's not wrong, it's not right either, obviously. So, similar to that is the dynamo hypothesis, which says that convective currents of plasma in the stars, those are what essentially lead to the magnetic fields. Now, if you say that, one question is, can a small scale dynamo generate fields that, so suppose I agree, suppose I take that there's a dynamo inside the core, so you the fluid is the plasma is rotating around the core, and from that small dynamo, what I need to agree with observation result is that the field should propagate through the layers of the star, reach the surface, and then behave in the way which we see. So from the core, we need appropriate transport and then appropriate behavior on the surface and beyond for this to be right. Now we come to the possibility hypothesis. What this says is that there's something going on during the formation itself. So stars form a very rough, dirty explanation. Stars form when molecular clouds aggregate, the gravitational pull is strong enough to pull the molecular debris, charged molecular debris, and then there's competition between gravitational pull and thermodynamic instability as well. But mainly, if the gravitational pull is strong enough, you get a protostar. Around that, some debris, which then later evolves to a star. So that's like, so during that formation, something is happening. What is that something? That feels the relics of that molecular cloud. So you have charged particles in the molecular cloud, and it's not plasma exactly, but as it aggregates closer and closer, it has some magnetic field system. You don't know what kind of magnetic field system there is, but as it aggregates and forms a protostar, the magnetic field of the molecular cloud remains. And then it later evolves to the kind of magnetic field you see. This is the basic idea of fossil field hypothesis. Now, the technicalities have to do with thermodynamic treatment or mostly magnetohydrodynamic treatment, MHD treatment of the molecular cloud. And then analytical studies are difficult, so mostly what people do is they try to simulate things. So they will start with some very simplistic model. So suppose introduce some field here, introduce some field there in the molecular cloud, and then let it evolve and see after some time if the results of the model agree with the observational results. So basically, as far as the physics is concerned, you would like to look at thermodynamics plus the magnetism of the molecular clouds and then evolve from there. So one particular note for these two is both the hypothesis is the stability of it. So you would see these two terms, toroidal fields and colloidal fields. So I don't know if I can draw. Okay. So imagine a donut. This is a donut. This this direction is the toroidal direction, and this direction is the colloidal direction. Colloidal direction. So toroidal and colloidal. So keep in mind what these two terms mean. We will see things. So so the depending on the system you are studying, you choose different reference frames or different coordinates and so on. So toroidal frame help while studying magnetic fields, so it's good to know that. So stability of fields is an issue. So when people did the simulations and involved them, they saw that stars with purely toroidal fields. So if this is the star and fields are just going this way, that is not stable. Stars with purely colloidal fields, that is also not stable. But linked, these two fields linked together, those can create stable star systems. Now, as I said, analytical studies are not exactly easy. So mostly numerical studies from 2004 till now, the main requirement was so to get a stable star at the end of the simulation, it has to be stably stratified. In the sense that some sections are majorly toroidal in nature, some sections are majorly colloidal in nature. And what I mean, I'll show you. So this is some snapshots of simulation which I was talking about. So you start with so it has to come from the inner layers of the star. The magnetic field lines travel through the layers of the star and evolve on the surface. So this is an example of nearly axis colloidal. This is all of that linked, but still it's stratified. So this the inner section, as you can see, mainly toroidal, but on the surface it's more or less colloidal. So that is like the real magnetic fields and observed on different stars is much more complex than that. But the point to appreciate here is that we have a stable field system for a star. starting from a model which we use. Now, there are time scales involved in this. So, the evolution of magnetic field from the inner layers to the surface has to happen around on the L time scale. This is I'm not going through the details of what this time scales apply, but the actual time is around 10 years or so. And then from the surface, the magnetic field die off. For all stars, neutron stars more significantly, but for all stars, magnetic fields die off, and that is known as magnetic diffusion. That will happen over a much longer time scale, which is 10 to 9 years. So, why do the magnetic fields decay? Come to that. But the time scales involved are such that the inner core of the surface has to be about order of 10 years or so, and then from there on, 10 to the power 9 years. Now, from now, we have seen that, like, so we had models, simulation and so on, and we matched with the observation data, and we saw that most agreement was found for possibility hypothesis. So keep that in mind. Now, I'll skip this. Okay, so this is important. So high field magnetic white dwarfs, low field magnetic white dwarfs. So there's this is convective zone, and this is the radiative zone, and this is the convective zone, and this is the localized radiative zones. So during the observations, what people saw was this: there can be field due to a dynamo, but which is localized in some region of the star. So it may so happen that the field system of the star has evolved as per the possibility hypothesis, but we have a dynamo generated field in a localized area which has effects as seen from the radiative zone. So dynamo fields have much uh, observed fields on the radiative zones of the stars. We see that in case of sun, but the point of this slide is it can be mixed. So you could have localized fields which have different behavior as predicted by either one of two hypotheses. So some statistics. So high field magnetic white dwarfs are much less in comparison. Low field are very high as observed, but and the masses also are different. The final state is like from the beam white dwarf core, you get to a magnetized white dwarf where the magnetic field is then decay on a much larger times. Now, the magnetic fields which we observe for white dwarf in particular are ordered in the sense that they are dipolar, but there can be quadrupolar and multipolar higher order components as well. So this we don't exactly know why it happens. Also, this statement very crucial that we don't have any field decay models for the field structures. So we don't exactly know why the fields decay once they get to the surface. So yeah, birth rates. So while so there was a note about difference in numbers. So high field models are very low, but low field were very high in numbers. So then people look at the birth rates of white dwarf stars and then try to figure out if something was there. Also, one key observation is that high field white dwarfs are rotating very slowly. So if you think about, so as there is a correlation between mass and luminosity of a star, you may wonder that if the star is rotating very quickly, chances are the field of the star will be much stronger. But here the observation is contradictory in the sense that high field magnetic white dwarfs are very slowly rotating, whereas the low field are very highly rotating. So the plot is the log V versus the period of rotation. So the comment about the dynamic hypothesis that post evolution from the molecular cloud, all memory of the residual magnetic field is getting wiped somehow. So since you are saying that the magnetic field which I have now is because of dynamo in the convective layers due to convective action in the layers of the star, it means that the magnetic field residue of the molecular cloud from which the star formed, the memory of that magnetic field is getting wiped completely, and then we are getting the field which we see because of dynamo action. This is the agreement from this argument is mostly seen for likely for low field magnetic white dwarf, but high field is finny. So after all that, quick summary. So there can be two cases. You start from formation. If the merger is very late, so uh, coalescing. If two bodies form and then they rotate around each other and then merge at the end. If the merger is late enough, then there is high chances of fossil field residue, and then those give high field magnetic white dwarfs with magnetic fields in this regime. If the stars are not non-magnetic, then they burn out and then give rise to what white dwarfs. Those are mostly low field white dwarfs. Another possible case is, so as I said, there could be either a binary system which then gives you one white dwarf, or a single star which could be magnetic, non-magnetic, whatever, but then it dies off, you get a white dwarf at the end. Memory of fossil field is lost completely, but there is some memory of fossil field. Then you have these possibilities. Now, sun, not this sun. So, sun is the has been the primary object of interest in so long in all aspects of astrophysics and astronomy. But magnetic fields in particular also heavy amount of study has been done. Before proceeding, a quick theme. So, core, thermonuclear reactions, and so on. You have radiative zones, photosphere. Then beyond photosphere, you have corona. Just below the photosphere, you can see arrows. That is the convective zone. That is where most of the action is taking place as far as the magnetic fields of sun is concerned. You can see sunspots and so on, so on. All kinds of radiation and so on. This is prominence too. As you can see from this picture itself, which is not complete at all, there's too much going on. But for our case, we'll restrict ourselves to these. So we look at sunspots, solar flares, coronal mass ejections, geomagnetic storms, and solar particle effects. So sunspots. This is what this region is known as an umbra. Surrounding that is penumbra. This cellular region is actually called granules, and there are boundaries. So, if you have seen a microscopic image of cells together, this is roughly what it looks like. And the model of study of granules is actually called automata model, cellular model. So, sunspots are particularly interesting in case of magnetic fields because this region, the umbra region, is cold in temperature, but very high, like this is the most dense region in terms of magnetic fields. So a lot of magnetic fields are going inside or outside in this region only, and mostly perpendicular to the sun surface. Around these, the magnetic fields are slanted to the surface, and the density is much lower. So sunspots in particular are events of interest. A quick tidbit, which is completely unrelated, is there the periodicity which you can see in solar cycle. So sunspots are periodic in nature. The period is about 10 to 12 years. Some people say 11 years, but it varies. Another event of interest vis-a-vis the magnetic fields of the sun is solar flares. This, now that those cool picture by the way. Credits to NASA, obviously. NASA is doing great stuff and very accessible, which is very good. So, solar flares, as you saw, and coronal mass ejections. So solar flares are rapid ejection of electromagnetic radiation, which happens near the sunspots. So there's a relation between sunspots and solar flares. That relation comes from the magnetic field of the system. The guy who, for the first time, gave the model of how the solar flares happen, related it with where sunspots occur. So that will come back. Coronal mass ejections. The picture you are seeing is a coronal graph picture. So the bright sun part is blocked out. You are just seeing the ejection of charged particles. So solar flare is ejection of radiation, but coronal mass ejection is ejection of charged particles in plasma. And these groups should be familiar by now, and we'll see. So, how is everything happening and how does it relate to magnetic field? So, side note, Elwin, that theorem, magnetic inclination. So, that theorem says that for an ideal conducting plasma, the magnetic fields are restricted to move along the plasma. So, if this tube is containing plasma and flowing in this direction, the field lines have to be this way. If I construct a boundary, and the flow of the fluid or plasma is this way, then the magnetic field lines will flow this way. That is that there. And the equation you see on the slide is the magnetic induction equation. So the change in magnetic field is so and so. The first term is the induction term and the second term is the diffusion term. And from here you can calculate a Reynolds number, magnetic Reynolds number. That will tell you whether that theorem is at play or not. So a quick and dirty introduction to magnetic reconnection. So, in few sentences, if I could say what magnetic reconnection is, it's the change in magnetic topology and breakdown of that field. That's it. That is magnetic reconnection. So, and magnetic reconnection happens in regions of neutral magnetic fields. So there will be sheets of, so in 3D, depending on however the flow is, you will get sheets with regions of zero magnetic fields, and those spots are where the Reynolds number will. So if in the region outside it, the Reynolds number is very high. So theorem which I mentioned, that holds for very high Reynolds number. For magnetic reconnection to occur and for that theorem to break down, around in that sheet, in that neutral sheet, in a very small region, the Reynolds number will become very small. And then, if the field lines are going this way along the sheet, in that region, they'll thread through the sheet. So, the topology of the magnetic fields is changing. This is a very simplistic and reductive uh, cartoon of magnetic reconnection, but what's happening is more or less this. So I like to call this solar magnetic field matter noodles because that's what they are. The action zone is actually boiling noodles. You can imagine. So keep the image of boiling noodles in your mind. This is the convective zone. The tubes are regions of high Reynolds number, so magnetic field lines are also flowing this way. The plasma is also flowing this way. So plasma is restricted to flow along the magnetic field lines. You have your noodle, as it rises above, it gives rise to loops. Loops. And when the loop rises high enough, these regions are the regions where magnetic reconnection occurs. So a shift in Reynolds number, shift in magnetic field topology, and this shift is accompanied by a huge release of energy. So Fields store energy. We accept that. So the energy stored in the magnetic fields of the plasma for hours or for days even, that gets released in an instant at these points, accompanied by a huge release of electromagnetic radiation and plasma. So you get electromagnetic radiation, which is solar flares, plasma, which is coronal mass flares. So noodle give you solar flares and CFEs. Uh, these are the loops and my drawing. Very good drawing. So loops are very fascinating. This is one image of uh, loops of from the sun, from trails. Amazing. So solar particle events. These are just ejections of charged particles from the sun. The graph is number of particles and time. So at some point in time, there's a huge increase in number of particles, and you see this because magnetic field has induced events which give you that. This is uh, a danger classification sort of in terms of the charged particles you get at Earth because that is harmful. Another phenomenon which is influenced by magnetic fields is solar wind. So he was showing me an animation before the talk. So sort of this Earth has its own magnetic field and solar wind, since it's essentially a stream of charged particles which generate their own magnetic fields, it interacts with Earth and it bends it. So there's a shock happening and all that. I'll not go into the details. So Go shock is happening and the field of the Earth bends. But the fact that Earth has its own magnetic field is the only thing which saves the Earth's atmosphere. Had it not, the atmosphere would have been blown up. So we are thankful for that. Uh, a geomagnetic storm is essentially that if the flare is strong enough, if the solar wind is strong enough, it can create a bunch of problems at Earth. Recently, in the past few months or so, there have been very strong solar flares if you have been following the news. So M class flares as well. So very strong solar flares even in the recent uh, months. So a small simulation for you. This is like you can do this sort of stuff once you get to modeling of the fields. So MHD is basically what's the tool you have, and from there, if the observations at the end of model is good enough, you keep that model, run simulation based on that model, and you get this sort of. So you could see sunspots that simulation as well. So I'll very quickly, since I'm running out of time, I'll very quickly go through neutron stars. So these are very exotic, very interesting areas for frontier physics, I'd say. And this slide is a bit misleading in the sense that not all neutron stars are magnetic, and not all magnetic neutron stars are the strongest magnets. So we'll see. A little history. You know S. Chandrasekhar, the Chandrasekhar limit. Uh, there is a point where beyond uh, that number, the white dwarfs cannot exist and they'll collapse. So those who are interested can read up on that. Chandrasekhar limit. This guy says that we can go beyond that with neutron being the pressure is there. He says not possible. Obviously, she comes in. We see. So what you see here is periodic uh, signals, like periodic increases in radio frequency, and that is what hinted at the existence of pulsars, which are basically neutron stars. So before this, so pulsars, as I mentioned, so not all neutron stars are magnetic, so on and so forth. So neutron stars are basically of three types: magnetars, which are particularly magnetic neutron stars; pulsars, which are also magnetic but not as strongly; and the this is the characteristic feature, and third hybrid, which is magnetic as well as emitting. So, quick look through the structure of the neutron stars. We don't know what happened at the core. So, neutron star is very dense. So, inner crust is mostly composed of heavy nuclei. This is more sometimes iron, sometimes even heavier. So, neutron much higher than iron. Then oh yeah. So and then the interior one there's neutrons. Then there's superfluid. So this is superconducting and superfluid. So superfluid is the fluid which has no resistance. Superconducting is no resistance. So this region is crazy in terms of the physics, the possibility of physics here. And the forces at play are gravitational forces, the neutron degeneracy pressure, and so on and so forth. These two are the primary. So some tidbits. Typical radius is only 10 kilometers. Earth's radius is 6,400 kilometers. Mass is about and condense it to about 10 kilometers. Density goes that high. Some factoids for you, and this statement is important for us. Magnetic fields can go as high as 10 raised to 15 volts. So Earth's magnetic field is about 1 Gauss, 1 Gauss. No, average Earth magnetic field is 0.5 Gauss. And average magnetic field on the sun's surface is about 1.5 Gauss. Look at this number here. So strongest magnets in the universe, definitely. So one important note that neutron stars are truly. Uh, you would have heard this, maybe not. If you are hearing this for the first time, I'm sorry for you. That eventually black holes too will evaporate and we'll experience a cold death. If you are hearing this for the first time, I'm very sorry. So neutron stars as well, they are slowing down and temperature is also reducing, but the time scales are not as the slowing down you can definitely notice, but the temperature difference is more or less noticeable compared to rotation. So these are the reaction, the decay happening for non-degenerate neutron proton, but neutron degeneration comes to play in the inner layers of the. So this is a pulsar. The white beams are X-ray emissions. The magnetic field lines are also rotated with the pulsar. So it's the magnetic field of pulsar is also dipolar as we see for what most many white dwarfs and for ours as well. And rotation axis is not aligned with the magnetic field axis. That is important. This model, the model of is called lighthouse model because lighthouse. Okay. So another thing to look at for pulsars is you like initial when we said modeling pulsars was done for spinning charge balls. So that's where it comes from. And the poles are where ejections happen. I'm not going into the details, but there is much happening here as well. You can see particle accelerations, spinning particles as well, some synchrotron emission, curvature radiation as well, and decay and pair production is also happening. So we'll leave it there. Another model is the outer gap model. So the light being emitted from the red area, since the pulsar is rotating, so you effectively get a light signature, and that is the outer gap model. This too much going on here as well. How do you see what's happening with the particles being ejected and how they interact with the magnetic field? There's also rotation to consider. So there's too much going on here as well, but yeah. So as I said, neutron stars are slowing down. The y-axis is the derivative of period, the x-axis is period. So the arrows, yeah. This is for mostly binary systems, but that is mostly for the supernova elements. Yeah. Uh, the shifts in period. So the period is growing. That means that the object is slowing down. So these are glitches, but overall you can see that the period is going as the year goes on. Pulsar glitches. So you can calculate the energy loss. This is a very rudimentary calculation. The This is just rotational kinetic energy. The change in that you calculate the change in that and then use the magnetic field at play to get a rough estimate of. So P prime is my notation for P dot. So it's I omega omega dot, and here is P dot. P is the period. So but even by this rough calculation of the energy loss and conserve the momentum, you can get an estimate of the magnetic field at play. G, what is the order of G? Whatever. So n is 90, the order of G. You can get an estimate of how high it is. Some similarities. So upper mean sequence, go back to the chart we had, the classification. So B is around that order, flux is around that order. Neutron stars, radius is much less. Magnetars is very high, flux is more or less the same. So the graph we had, period derivative, period. These are millisecond pulsars. So pulsars are rotating with different speeds. So millisecond pulsars are by in each millisecond you get a blip because the beam passes through all points. So these are millisecond pulsars, classical pulsars, and magnetars are up high in the corner. So that high means the change is that much. So it's slowing them down very rapidly. So there's some calculation on the spin down spinning of and some estimate of the time scale of rotation decay. A quick comment on the origin of neutron star fields. Again, we'll go. So the major ideas remain the same: fossil field, dynamo, and one more is because of the peculiarities of the neutron star, thermodynamic instability can also produce fields high enough. But the problem is it's restricted to the surface. So what's happening here is degenerate electrons are moving at very high speeds, and due to that, on the crust of the neutron star, the degenerate electrons are moving so high, so quickly that the field generated are they grow exponentially over a very short distance. But the problem is they are restricted to the crust of the surface, and still the field is this magnitude doesn't reach less than 15, which is an issue. How do we know that the magnetic field system is not static and evolving? Because obviously, since its rotation speed is going down, uh, that has to have some effect. Also, magnetic field decays. How do we know that? Because the current idea is that magnetic field decay is the main analysis, and stable magnetic fields have not been observed for neutron stars. This is some rudimentary models for neutron stars, some magnetic configurations. Pure colloidal and pure colloidal obviously, as for the case of stars, even for neutron stars, not possible. Mixed is the answer, and only together can they stabilize each other. But we don't exactly know what's happening. This is again, so this is the signal with which you detect neutron star. So this is the period and the intensity of the function of time. So you see blips depending on whichever regime you are operating, X-ray, optical, or whatever. X-ray, gamma, and optical. So you see blips. Those blips are more the signals. These are gamma ray pulsars. Again, the frequency and the intensity. So some pictures for pulsars. Crab nebula is a famous astronomical object. The accretion disk, the accretion disk is not a proper term, but still, the pulsar wind in a toroidal shape around the pulsar. Pulsar is in the center, and you can see jets from the. This is from the supernova, and this is the crab pulsar. Now, a very quick run through the everything. So, in summary, what do we know? We know how to observe. We can use magnetograms, Doppler imaging, time series spectroscopy, spectrofluorimetry. We know how to observe, and then we can calculate magnetic field maps. Once we know the magnetic field maps, we think about how it all happens, how magnetic field originates. So three hypotheses, possible hypotheses, remnants of the residue of the molecular cloud during formation. That's what's giving you. Second one, dynamics. Convective currents, those charged plasma moving inside the layer of this star. That's what gives you the magnetic fields. Third one, thermoelectric instability. Only in case of neutron stars, but electrons moving on the surface, magnetic field also will on the surface. You know what? Then we saw some effects. For the sun, we saw sunspots, we saw solar flares, CMEs, SPEs, we saw solar wind. We also have some idea of effects on space weather and so on, and interaction with planetary fields. For stars, so sunspots, stars are now using star spots. Injections also you can have, and radiation bursts, as the case of neutron stars. Now, possibly the most important part of this talk, which is beyond this. Uh, Obviously, I have skipped a lot of things, and the level of detail is not as high. But these are the things which I would like to encourage people to read up on, those whoever are interested. So, observation details. One thing I showed you was how to calculate B from polarization, but I went through quickly because first interest of time and then complication involved. So, model of atmosphere, very tricky things to do. So, details of observation, if you want it, you can check it out. Origin. So, star forming regions, the possibility hypothesis, a very rich area of physics, not much observation data available, like direct observation data available, but still interesting physics. Like with models, you can do a lot, even though you may not get models which agree with observational data, but at least the physics you can study beforehand. Then for the existing fields, mostly this is being done statistical evaluation because analytical is not possible. Lots of things are happening because there is drag to consider. Now imagine where the system in play is plasma of the convectiveness of the sun. There's drag to consider, there's temperature to consider, magnetic tension to consider, and quantum mechanical effects to consider, and so on and so forth. So mostly statistical evolution and M.Sc obviously. Magnetic reconnection, which I hinted at very roughly though, very interesting areas, and we should definitely check it out. Just like even if you don't spend an hour, just Google it up and see what's happening. So that is very interesting. And then more stars which are interesting usually the magnetic fields. So I just discussed white dwarfs and sun. You can have Tauri stars. I skipped on massive stars because we didn't have much time. Also, you can study binary systems. And then things complicate from here as well. Lastly, this is very crucial with very immediate effects. So, solar wind in our proximity and beyond the sun, the effects of stars magnetic on the planets around it or other bodies, especially in binaries. That is very interesting. And lastly, the king of the hills, neutron stars, very exotic and very interesting. You should definitely Google it and study, read up more. That's it. So questions? a bit exhaustive, but